Hello friends, welcome to Susan and John MathTube. In this video, we are going to learn another powerful method to find inverse set transform. Okay, in the last video we learned partial fraction method. But this method is even more powerful than the partial fraction method, and it's called inverse integral method or the residue method. But the sad news is this method is not for every student. This method is only for those students who learned complex analysis and those who know about poles, singularities and calculation of residue. So if you know how to calculate the residue, you can enjoy this method. Anyway, let me introduce you to this notation once more. ZTransform will convert sequence into functions in the letter called Z. And the inverse will convert functions in Z back to the sequence or a sequence generator. Anyway, the statement you see here and the statement you see here are equivalent. Okay, now look at this. I want you to be very clear with this because when you go for the exam and if someone uses a different notation, you should not get worried about it. So the input can be denoted by the sequence generator can be denoted by x of k, x of n, f of k, etc. etc. And output is denoted by, output means when we take the set transform, capital X of Z, capital F of Z, and that's exactly what we are following here. Anyway, in the videos, I am trying to follow this and this. However, in many books, it's common that they use X of n. Can you see? This is the sequence generator or the sequence or the general term of the sequence. And by taking Z transform, we convert it into a function of Z. And by taking Z inverse, we reach the sequence generator. By the way, subscribe to our channel, like the videos and support us. Okay, now let's go for the method. Okay, now don't get worried about it. If they ask you the statement of the inverse integration method, you can copy this. So this comes from the formula. Can you see? We are trying to take the Z inverse of a function and it's given by a complex integral and the contour is given below. I think you can read the contour. I want you to take a screenshot so that you can keep it for the statement. Anyway, don't get worried by looking at this integral. I have a very easy method for you. Again, I'll minimize the screen. So take a print screen. And if possible, you can keep a printout also. Just follow this working rule and you'll be able to solve most of the problems in which you want to calculate Z inverse. And like I told you, one of the best application of the Z transform is solving difference equation. And when you solve difference equation, eventually you'll reach a step where you have to take the Z inverse. And at that point, this working rule will be very useful for you. Anyway, the given function is, we are taking Z inverse, right? So the given function will be a function in Z. You can denote it by capital F of Z, you can denote it by capital X of Z unless it is given. Now what you do is multiply throughout by or multiply both sides by Z to the power k minus 1. Come on, do you remember? In partial fraction I asked you to multiply by 1 by Z. In residue method or the inverse integral method, you multiply by Z to the power k minus 1. Don't forget that. Anyway, eventually you will get the function called Z power k minus 1 multiplied by X of Z. Anyway, now find the singularity, residue, super easy, add them up. Because the 2 pi I and 2 pi will get cancelled and you add them up. Okay, let's start with the problem. Be ready with the pen and paper. Let's start. Okay, we have a question here. Find the inverse Z transform of xz equal to z divided by z square plus 15z minus 34. By the way, don't use partial fraction method because it is clearly given in the question using residue method. In examination, if they do not specify the method, it's up to you. But if they specify the method, use convolution, use long division, use residue method, use partial fraction method, then you don't have an option. Anyway, let's go for the residue method. So what did I do? I am calling the given function. No, it's already given. If it is not given, I will name it. Now step number 2. Do you have the working rule? I have kept the rule over here. Given function, multiply, singularity, residue, add them up. So I'm going to write multiplying both sides by z to the power k minus 1. I hope you remember the laws of indices. What is a power m times a power n? You have to add the powers. So suppose you want to multiply z to the power k minus 1 with z square. It will become z to the power k minus 1 plus 2, which will be z to the power k plus 1. So what happened in the right hand side is z power k minus 1 plus 1, which happens to be z power k. So step number 1, give it a name. Step number 2, multiply both sides by z power k minus 1 and simplify. Now I factorized. Now time to write the singularities. Come on, you did a lot of problems in complex. So what are the singularities? What are the singularities? Z equal to 2, Z equal to minus 17. And I have to write symbol pole, symbol pole. Come on, now it's just residue calculation. So I'm going to do it over here. R1 equal to residue at Z equal to 2. Do you still remember the formula? Limit Z tends to 2, Z minus 2, Z power k by Z minus 2 into Z plus 17, cut, and this will become 2 to the power k the whole divided by 19. Similarly, residue at the second point, the second singularity, the second pole, residue at Z equal to minus 17. That will be limit Z tends to minus 17, Z minus minus 17, that will be Z plus 17, the divided by, and you're going to get minus 17 the whole power k by minus 19. Now the last step. The required sequence will be sum of the residues. And that's it. I just added the residues. Now let's do some more interesting problems. Do you want to try? So pause the video, try it. The sequence B. Why did I write let the sequence be here? When you take Z inverse, the answer will be a sequence. If you name this function, you have to call it function of Z. Anyway, I found the singularities, and the singularities are 2 and minus 3, pole of order 1, order 2. No, you're doing a big mistake. Don't do this in your exam. Don't do this in your exam. In excitement, many students do this mistake. Can you tell me what is the mistake that I made? Step number 1, call the given function as capital X of Z. Step number 2 is not calculating the singularity or the residue. Step number 2 is multiplying both sides by Z power k minus 1. So I multiplied both sides by Z power k minus 1. I calculated the singularities. I'm calculating the first one is a symbol pole, so I'll cut down the drama. I calculated residue 1. I hope you got the same answer. And now I'm going for the second pole. The second pole is of order 2. I hope you noticed that one. The second pole is of order 2. So I applied the formula 1 by order minus 1 factorial. Differentiate order minus 1 times the same thing. Now I have to do differentiation. So limit Z tends to minus 3. What's the derivative of this stuff? Denominator k Z power k minus 1 minus numerator multiplied by 1 the whole divided by Z minus 2 the whole square. and that is going to give me minus 3 minus 2, that will be minus 5 k times minus 3 the whole power k minus 1 minus minus 3 the whole power k, the whole divided by minus 3 minus 2 the whole square, and we are done. Now we have to add the residue, but let me simplify this a little bit. By the way, do you remember a power m plus n is a power m times a power n. So I am going to get this as minus 5 multiplied by k minus 3 the whole power k multiplied by minus 3 minus minus 3 the whole power k. I hope it's not confusing you. And here k minus 1, so I have to put minus 1 here, divided by 25. Once more, if you are confused, I'll put it like this: minus 3 the whole power k minus 1. It splits and it becomes minus 3 the whole power k minus 3 the whole power minus 1. It's just basic simplification. So we get minus 5 multiplied by minus 3 the whole power minus 1 multiplied by k minus 3 the whole power k divided by 25 minus minus 3 the whole power k divided by 25, and this will cancel and this will go to the denominator, and we end up like minus 1 by 15 k into minus 3 the whole power k minus minus 3 the whole power k by 25. It's better to simplify as much as possible. Anyway, check whether the last answer is this. How did I get the last answer? You have to add all the residues. So let me tell the steps once more. It's super easy. What's the first thing to do? Call the function as x of z. Second thing, in partial fraction method, you'll multiply both sides by 1 by z. Don't forget. In residue method, you'll multiply both sides by z power k minus 1. Now let's go for another very important problem. Extra important problem. Maybe they will ask this directly, or maybe you'll have to use this when you're learning the application. That's a difference equation. Anyway, as always, I called it x of z. Now what should I do? Don't forget, what should I do next? Okay, very nice. Multiplying both sides by z power k minus 1. And that is going to give me z power k divided by z square minus 2z plus 2. Don't forget this step. And then, as always, the singularities are given by denominator equal to 0. You can use a calculator, and if you don't want to use a calculator, use a formula minus b plus minus root under b square minus 4ac by 2a. That formula. And good news, we got symbol pole. The poles are z equal to 1 plus I, z equal to 1 minus I. Anyway, my recommendation is use a calculator unless you end up with equations which has I. You cannot input these stuff into your calculator, but here it's okay. A is 1, B is minus 2, C is 2. So strongly recommending use a calculator. And I hope you remember the factorization method. How do you factorize the quadratic? A multiplied by, don't forget, A multiplied by z minus alpha, z minus beta, where it's a root. So I can factorize the denominator now. Now let's start calculating the residues. So R1 equal to, it's a symbol pole. So limit z tends to, come on, tell me who is the first pole? 1 plus I. And z minus bracket 1 plus I. We already know the denominator, z minus 1 plus I. You can also see this here. Z minus 1 minus I. Now let me go and check the numerator. What's the numerator? What's the numerator? The numerator is, yeah, z power k. Because I multiplied both sides by z power k minus 1. So the numerator is going to be z power k. So this will get cancelled. So R1 equal to 1 plus I, the whole power k, whole divided by 1 plus I minus bracket 1 minus I. 1 and 1 will get cancelled. So I'm going to get 1 plus I, the whole power k, the whole divided by 2i. So note it down somewhere very clearly, because at the end we have to add all of them. So 1 plus I the whole power k, the whole divided by 2i. That's the first residue. Similarly, let's go for the second calculation, R2. That's also simple pole, so it's fun to calculate. Limit z tends to 1 minus I, z power k divided by, I'll cut the drama because one factor will get cancelled, so you'll get z minus 1 plus I over here. That will be 1 minus I the whole power k divided by, let's see, 1 minus I minus bracket 1 plus I. So 1 and 1 will get cancelled, but we'll get minus 2i over here. Anyway, at the end you're going to get this. So sum of the residue 1 by 2, I took common. I think you saw the residues over here. Can you see the denominator is 2i, denominator is minus 2i. That created a negative over here. Now wait a minute. When we did partial fraction also, I told you never ever leave your answer like this. In examination you might get excited and think, okay, that's the last answer. No, this is not the last answer. Whenever you get a complex number, you have to convert it into modulus argument form and try to simplify. I hope you remember this. If not, I'll strongly recommend you take a screenshot. You can convert any complex number into r e power I theta using this method. If it is on the axis 0 degree, 90 degree, 180 degree, minus pi by 2. If it is in the quadrant, if it is between 0 and 90, first quadrant, second, third, use the formula, and r is given by this. Okay. So 1 plus I means 1 comma 1. It is in the first quadrant. So the length will be, r will be root under 1 square plus 1 square, that will be root 2. And the angle is tan inverse positive value of 1 by 1, that happens to be pi by 4. So I can easily write 1 plus I is root 2 e to the power I pi by 4. Now I have one more complex number, that is 1 minus I. So I'll go for 1 minus I. 1 minus I is 1 comma minus 1. Where is 1 comma minus 1? That is in the fourth quadrant. So the length is root under 1 square plus minus 1 the whole square. That's the same, root 2. Now the angle is theta is equal to, did you see this table? Yeah, minus tan inverse positive value of minus 1 by 1, which happens to be theta equal to minus tan inverse 1 minus pi by 4. So this 1 minus I is actually root 2 e to the power minus I pi by 4. So we have the answer x of k equal to, do you remember the answer? 1 by 2i. This is what we got. The whole power k minus 1 minus I, the whole power k. Do you remember? We added the residues. Now I'll plug it here. 1 by 2i e to the power I pi by 4, the whole power k, minus e to the power minus I pi by 4, the whole power k. For students who learn complex properly, this will be like super easy. And e to the power I k pi by 4. Comment below whether these videos are useful for you, and make sure you do a lot of practice. So 1 by 2i. Come on, now you tell me, what is e to the power I theta? Cos k pi by 4 plus I sin k pi by 4 minus bracket cos k pi by 4 minus I sin k pi by 4. So this cos and cos gets cancelled, and this will get added up. So you'll get 1 by 2i. What is apple plus apple? 2i sin k pi by 4. So apple plus apple is 2 apple. So this will get cancelled, and sin k pi by 4. Now something very important. Time to practice. I'll give you 3 questions. Do it now itself. Don't be lazy. This is extra important, because what happened just now is you are able to understand the concept. But if you want marks, you have to practice. And can you see the first question? Second question, I have given some hint. And the third question is a challenging question. I have kept the answer. Try it and tell me whether you got the answer or not. It's a little bit when you differentiate. Okay, I'll pin the answer in the comments later. So I'll be back with something very important, that is called solving a difference equation with Z transform. So till then, my friends, bye.